Welcome back. Today's information and topic is on basic motor control and motor terminology. Now, there's a couple of different categories of devices that we're going to go through today. We're going to look at pilot devices and indicating devices, and basically what is a pilot device and where does it fit into the control scheme. And then we'll talk about some devices that actually turn electricity into motion. So there's a couple different motor types that we'll touch on, but we will get a lot more information on those two motor types, stepper motors and servo motors, in a later presentation. So when we talk about control devices, there are some devices that are considered primary control devices and some that are considered pilot control devices. So when we talk about primary control devices, we're talking about components that are primarily controlling the flow of current to the motor. So we're connecting the electrical power from the power line through this device, and then the current will reach the motor and the motor will function. So sometimes we connect across the line, which means that all of the voltage that is coming from the power line connection goes directly to the motor, and there's no reduced voltage or other things that happen, no current limiting or anything of that matter. So contactors, starters, controllers, variable frequency drives, things like that are considered primary control devices. Now, a pilot control device is some type of switch or sensor, or it could be a control relay or something that closes the connection between the electricity and the motor coil, or actually the motor starter coil, to control the primary control device. Or it could be something like a switch that's connected to a variable frequency drive as the primary control device. So it is essentially something that has just two connections to it. It's sort of an in and out type situation where the switch or the contact or the sensor will close that connection, turn on the power to the primary control device. A common type of pilot device is a toggle switch, and you don't often see that on a more sophisticated control circuit, but it's worth talking about the different types of toggle switches. Now, basically, what's called a toggle switch, or what is referred to as a toggle switch, is a switch that has a lever, and it is operated manually by hand, in other words. And there are different configurations, as you've learned in basic electronics: single pull, single throw, single pull, double throw, double pull, single throw, and double pull, double throw, among many different types. So the pulls are considered the input side, although you can use a single pull, single throw either direction and it doesn't matter. It does on these other ones. But single pull means that there is one movable set of contacts per circuit. Double pull means that there are two movable contacts per circuit. Now, the throws are the number of outputs per input. So a single throw means that there is just one output, one possible connection. So that's either on or off. Now, a double throw means that we can connect to one of two outputs. So a double throw would connect to one output or the other depending upon the position of the switch. Generally, we can only have 2 throws on a toggle switch. If we want more than 2 throws, we need a rotary switch or something else, some other kind of configuration. When you replace a switch, it's important that you replace the switch based on its rating. How much is the maximum voltage that needs to be interrupted or stopped, and the amount of current that the contacts will handle. Now, the AC current rating is higher than DC because AC turns off, the current stops twice every cycle. However, DC, the current remains constant. So if you're looking at the rating of a switch that is rated for alternating current, you cannot use that same level if you're switching direct current. So here's a little bit about how we can look at the switch contacts. If you're using a switch for AC, or if it's rated for AC, but you're using it on DC, then what you need to do is basically derate or reduce its rating to about 60 to 70%. And that's important because in DC, when that current is flowing, when you break that current flow, if the switch is not rated to interrupt that amount of current, then it could continue to arc and you would continue to have current flow. And arcs will destroy the switch, and so that's a bad situation no matter what. Now, if it's rated for DC use, you can use it in AC circuits up to the rating of the switch. So in other words, if it's rated to disconnect 250 volts DC, you can use it in AC circuits up to 250 volts. If it has a 10 amp contact rating in DC, then you can use it in an AC circuit to interrupt up to 10 amps of current flow. So you can also use switches for any voltage or any current that's less than its rating, as long as the same type of current is present. So in other words, if you have a circuit that runs on 12 volts and switches 5 amps, DC, if you had a DC switch that could run on 100 volts and switch 10 amps, well, that would work because the actual condition is less than its rating. But if you have a switch that's rated for DC use and you use it on AC or vice versa, then sometimes you have to derate the switch, and you can see how you derate it on the slide here that you're looking at. Another pilot device is the push button switch. Those are commonly used for motor control applications, and they're commonly found on control panels and operator panels and things like that. And most often, push button switches are momentary, but sometimes they can be maintained. Now, we'll talk about that in just a minute. So on this, you have 2 different switches. You have a normally open and a normally closed push button switch. Now, the NEMA symbol is the symbol that you're having to memorize for this class. The IEC symbol is what you would find on schematic diagrams and wiring diagrams and ladder diagrams that are in equipment that's made outside North America. So they just show that to show you the difference between how the two look. And remember, the normally open One will not have current flow until it is pushed or pressed. The normally closed will have current flow through it until it is pressed. There's a type of push button called a brake make push button, and that uses the same movable contacts for the normally closed portion as it does the normally open portion. When we need to switch between the control of one circuit to another, then we can use a brake make push button. This is an example of a circuit that uses a brake make. So when the jog push button, which is the brake make push button, is not pressed, this will function like three-wire control. You push the start button, the motor contactor coil energizes, the sealing or holding contact that's across or in parallel with the start push button is closed, and when you release the start button, the circuit will continue to operate. Now, when we push the jog push button, basically we're taking over the three-wire control and turning it into two-wire control. So when we push that jog push button, then it will cause current to flow to the motor coil. And in this case, what happens is that when we release the jog push button, that's enough time for the motor coil or the motor starter coil to lose its magnetism. And so it resets the three-wire control to off. So this is a circuit that operates in three-wire control until you press the jog push button. And then it turns into two-wire control. And when the jog push button is released, then the circuit will no longer work. This also allows you to operate the circuit in two-wire control. You can have the motor run just by pushing the jog push button. So in that respect, the jog push button allows two-wire control. And then when you release the push button, then that will bring the circuit back to its off position or its off condition. Now, what jog means is that's a technical term that means we're going to operate the motor for a short amount of time. Maybe we want to move a conveyor belt a little bit and allow the product to move a couple feet down the conveyor belt, and that's it. We don't want a continuous operation of the motor. We would consider that as jog or jogging. One other use of jog is when we have a hoist or a crane, or maybe it's a movable device, and we just want to create a little bit of motion for a short amount of time. Then we can push a jog control, and that operates the motor for a short amount of time. And again, this is a brake make circuit. And essentially the way this works is that when you push the brake make push button, the red pilot light that is normally glowing stops glowing and the green pilot light will glow. So this is just a test circuit to show how a brake make push button operates. Now when you attach a push button device or any kind of switch or control, we have to put it in some type of an enclosure. Sometimes it's a control panel that inside has other components. It could have relays and contactors and other devices that are inside. It could have time delay relays or whatever. Or we might have, like this, is a start-stop push button station, an operator control station where the two push buttons are mounted in their own enclosure. Now, there are different types of enclosures depending upon where they are being used. And the types of enclosures are used in those different locations. And when you need to buy one from scratch or replace one that's damaged, you need to order the correct enclosure type. And the type of enclosures are standardized by the National Electrical Manufacturers Association, or NEMA. Now, this shows you where the different types of enclosures are used and the conditions in which they are required. So a NEMA type 1 is used in an indoor application where you're not expecting dust or vapors or liquids to get on it, because they don't really have a lot of protection from the outside elements. They're basically just enclosing the circuitry so people can't get their fingers in where they're not supposed to be. But then you have a number of different types, and some of those are for locations where there could be explosive vapors or gases present. There's some that are used outside when you have severe weather conditions. There are some that are really enclosed and sealed against dirt and dust and explosive particles. So, for example, when you're using one of these control circuits in an environment like, let's say it's a mill that takes wheat and grinds it down into flour, that flour is such a fine particle and it is flammable that when we have a lot of that dust in the air, a spark could cause an explosion. It's the same thing in paper manufacturing. So when we make paper and we cut the paper, that makes paper dust. And that paper dust is extremely flammable and extremely explosive if it is concentrated in the air. So there are conditions where we want an explosion proof or a sealed enclosure that if there's a spark inside of it, that spark will not ignite the vapors or the dusts or other flammable materials that are around it. And it's not just when we're using spray paint in a spray booth, where we have lots of flammable vapors coming from the spray guns. It could also be other situations. And so that's one of the reasons why when they have situations that are dangerous or hazardous, they really need to be designed by engineers that understand all of the safety factors that need to be engineered into the circuits. But if you take a look at this, you'll see that there are a number of different types of enclosures. And if you're the person that needs to replace one, then you need to replace it with the same type of enclosure that it was originally designed with. Now, when you buy a push button switch, you can actually buy them in their individual components. So the part that the operator, the person that's operating the piece of equipment, comes in contact with is called the operator of the push button switch. Or other types of switches, such as mushroomed head switches or emergency stop switches or selector switches, they can also come in different pieces. So you can buy the operator type that you want. And then you will have some type of a contact block. It could be already built into the switch itself, or it could be like the one you see up at the top of the slide, where you can take and stack multiple contact blocks on top of each other to have the switch configuration that you want. So you're not necessarily having to buy just one normally closed push button switch, and that's the only connection that you have. But you can add these contact blocks, just stack them one on top of the other or put them one on either side, and those will make the switch into the configuration that you want it. And you can also buy legend plates. A legend plate is pre-printed with the function of the switch. Could be stop, start, reset, emergency stop, jog. There are any number of ones that are already made, but then you can also have them custom engraved for the application that you want. Here's some of the different types of operators that we can have. We can have one that is stacking a start-stop push button in the same operator, and then you would have one contact block that would be activated when you push that green button, and then you'd have a different contact block that would operate when you push that red button. The one next to it is a mushroomed head, and remember, we use those as a quick, fast way of having the operator just slam his or her palm into it, and that will activate the switch. We can have regular push buttons like the third one from the left. Sometimes we can buy those with the head of the push button recessed back so that there is no chance for somebody to accidentally come in contact with it. Sometimes we can get those with the head sticking out further for like a stop button where you want easier access to be able to stop it quickly in an emergency. And sometimes we'll have other ones that look different, like the one at the far right, that exit operator, and they can make those in different shapes and different configurations. And here is a couple examples of the legend plates that we've talked about. Here are a couple of different types of contact blocks. The one at the far left top, that is colored red. And when you see the red ones, the red usually means it's normally closed. Because remember, on a push button 3-wire control, the stop button is red, and that is a normally closed contact. You can also see on the side of the contact block, it says NC. The one right below it, I can't tell what it is unless I look at the labeling, which is probably on the other side. The one at the upper right hand, or the three that you see up there, the ones that are yellow, if you take a look at the yellow ones, you'll notice that they have 4 contacts. So 2 of those contacts are normally closed, 2 are normally open. That would make that a break-make contact block. And then the one below that at the right actually has 2 contact blocks built in. It has a normally open and a normally closed. And that might be the type of contact block you would use for that operator that has the green and the red push button built into it, the start and stop push button operator. Now, when you buy them, the standard configuration is having a normally open and a normally closed one within each of the contact blocks. And those would be break-make switches, but we don't necessarily need to use them as in a break-make configuration or break-make circuit. We would use the contacts that we need. So let's say we only need a normally open contact, we would just use those and not connect to the normally closed contact. And vice versa, if we only needed a normally closed contact, we would connect to that, and the normally open contact we would leave disconnected. Now, this also shows that we can stack multiple contact blocks on top of each other. So in this case, what happens when you push this operator, that moves these contacts inside the first contact block. But there's also a lever or a bar that is going to push or transfer that motion to the additional contact block. And it will have the same thing inside. So when this button is pressed, a little tab is going to push out of the end of it, and then that can push the next contact block. So we can stack 2 or 3 or 4 of them depending upon how strong the springs are. You know, if we get a whole bunch of them in there, it adds it adds to the amount of force that needs to press the switch. So after we stack, you know, maybe 3 or 4 of them, then that switch is going to be too difficult to press. So in that case, we may need to build the rest of the contacts by using control relays rather than just relying on the switch itself. The contact blocks are all have springs associated with them inside, and that spring returns them to their normal state. Now, if you want the contact to stay, then you're going to have an operator that is called a maintained operator. We'll see that in just a little bit. But all contact blocks have a spring that returns them back to where they were initially. Now there's a type of switch that we've talked about before, and we'll cover it again, that is called a maintained switch or a maintained control. Now that means that it stays in the position that you activate it in. So for example, like this emergency stop switch, when you push the lever or the button on that device, it mechanically locks into the position that you want it to be in. And then sometimes we have to turn it or pull it or put a key into it to have it return to its normal condition. So maintained means that it stays in the position that you place it. Now here's where an emergency stop circuit push button would be placed in the 3-wire control circuit. It's in series with the circuit. Also, it often is in addition to the regular stop button. It has a mushroomed head. It sticks out from the surface of the control panel or the enclosure, and it will stay off until it has been reset. Here's the same type of circuit that's shown on the constructor software, and you'll just see where it goes in the 3-wire control configuration. Now, something that's not considered a pilot device, but it is usually incorporated in the control circuit, is called a pilot light. Now, they provide a visual indication of what's going on in the process. You can get the lenses in different colors, and what's interesting to know is that the color of those pilot lights are often determined by the overall engineering of the facility. Sometimes a green light means that the circuit is off and safe. Other times, a green light will mean that the circuit is on and functioning. So that's why there's usually a legend plate or some type of labeling above each pilot light so that you know exactly what it indicates. Now remember, there's also a device that's called an annunciator. And the annunciator, its purpose is having multiple pilot lights behind a front panel that each light has a label on it so that when that area glows, you read exactly what condition is happening. Some of those pilot lights on an annunciator, they come on for good things like the circuit is operating properly, you have proper pressures, proper temperatures. Other times, a pilot light in an annunciator panel is going to show you when you have a bad condition or a potentially catastrophic condition. They will also sometimes come on when servicing needs to happen, to let the operator know that it's time to change a filter or perform a preventative maintenance operation. Now, what we're doing in recent times is we're replacing annunciator panels with HMI panels, human machine interface panels. And it's basically a computer screen that has symbols, and it may show you the process flow. And what happens is that those panels usually are touch sensitive. So you'll press on one of the pictures or symbols or icons, and then a different menu will come up and show you more specifics. So those HMI panels are starting to replace the push button switches that you're seeing and the pilot lights that you're seeing and the selector switches that you're seeing. So those HMI panels are connected to the controller or the PLC that is operating that piece of equipment. Now this diagram is showing a start-stop push button circuit, a 3-wire control, and it's showing a pilot light as part of that circuit. And when the starter is energized, that's when the pilot light will show up and it will glow. So you see that where they place it in the circuit is there, because it's a load, they're placing it on the right-hand side of the ladder diagram, and it's in parallel with the motor starter coil. So when the motor starter coil is energized, that same voltage is going to the pilot light, so the pilot light will glow. And generally when we put pilot lights into a circuit, we're either putting them in parallel with coils of contactors or relays, or we may have a separate rung where the pilot light goes through one of the relay contacts and gets its power that way. Here's the same type of circuit that's shown on the slide before it that is in the constructor software format. Now, one of the things that we can do to allow a pilot light to be energized, as I've said just a moment ago, is that we can use a relay contact to do that. Now, when we have a contactor in a starter or some other control device, one of the things that we can do is either buy that contactor with extra contacts, auxiliary contacts they call those, or we can snap on an auxiliary contact block on the side of the contactor. Now, just about every contactor has that capability, but some don't. So if you're trying to add to the control circuit, you either need to buy an additional contact block that snaps onto the starter relay or starter contactor, or you have to replace it with one that has the auxiliary contacts already built into it in the quantity that you're going to need for that circuit. This also shows that circuit that has the auxiliary contact being used for the green light. And basically, as you see at the bottom of that diagram, there is an auxiliary contact in that motor starter contactor. The M contact that's right at the bottom that is normally closed. The green pilot light will turn on until that coil in the motor starter is energized. At that point, then, because the coil is energized, the normally closed M contact with the green pilot light, that will open up and the green light will come off. But because the starter coil is energized and because the red pilot light is in parallel with that, you will end up with the red light glowing when it's operating. And of course, when it's not operating, the green light will turn on. But as I've said before, sometimes they'll switch those around. The red light will mean that it is not running, and the green light will mean that it's running. It just depends on how they've designed the controls for that piece of equipment or that portion of the industrial facility. There's sometimes when we want to have a pilot light operate at a lower voltage than the control circuit. So what you can find are pilot light holders, sockets, that have a built-in transformer that will take the high voltage and bring it down into a lower voltage. Now, that works when your control circuit runs on AC, but when it runs on DC, obviously we don't use a transformer. Sometimes they'll put a resistor in the circuit, and that will allow a low voltage lamp to be operated with a higher voltage control circuit. Another thing that they're doing is replacing the incandescent bulbs, the bulbs that have filaments in it, the old traditional style of light bulbs. They're replacing those with LEDs, which take less current and make far less heat than you have for incandescent bulbs. They also last anywhere from 30, 50, 100 times longer. In some cases, they will outlast the piece of equipment that it's being used on. There is a type of lamp that is called a push-to-test pilot light. And essentially what happens with that is that it is where you can push the lens of the light in, and that changes a switch inside. So normally, with it not being pressed, it will be connected to the circuit that is energizing it. But when you press it in, it removes that connection and instead connects the light directly to power, and then the light should glow. So when you push one of those push to test pilot lights and it doesn't glow when you press it, probably the bulb is burned out, the lamp is burned out. Or it could be that there's no power to the circuit itself. But likely you're going to have a bad bulb in that situation. In a critical environment where when a light comes on that shows a dangerous condition, you want to make sure that you test that every so often. Sometimes it's part of the beginning of a shift of a worker, an operator. That worker is going to test all the lamps to make sure that they're in working order. Here's the same circuit shown on the constructor. There is another type of switch called a selector switch, and allows us to control which circuit is being utilized. So for example, this one shows a selector switch being used for hand off automatic, HOA. Now when it's on the selected position of hand, then it will turn on itself. It will be, you can operate that motor or that piece of equipment by itself. Sometimes, like in this one, it will actually have, when you put it on hand operation, it'll have another switch that allows you to activate the circuit. So it would be for testing purposes, or if you needed to run the circuit for a little bit to change a certain condition, then you would have it on the hand position. When it's on automatic, then the pilot device, in this case, a level switch, is activated. So the circuit will only work, or the motor or whatever we're controlling will be turned on only when that switch is closed, that liquid level switch. When it's on the off position or in the off position, then that means that neither manual or automatic is possible. It means that you've shut that piece of equipment off completely. And you can do that if you need to load something into that equipment, load materials, or if you need to do a change of some kind. It's not meant for servicing. Remember, when you service something, when you're repairing it, you're going to follow lockout, tagout procedures. And oftentimes, you won't have that opportunity to lock out a selector switch. In fact, selector switches are really discouraged from being used as lockout points. One thing you'll see with a selector switch is that they will put a table next to there to show which position has which contacts connected. So in this case, there are 3 positions. When it's on position 1, contact block A will close. When it's on position 3, contact block B will close. When it's on the second position, the middle position, neither one are connected. Now, these are very important when you're trying to figure out how a circuit works electrically. You can figure it out probably by looking at the diagram, but having that table explaining it to you is pretty helpful as well. Now, this same circuit is shown on the constructor as it is with the ladder diagram before. Remember that what we're doing is allowing the piece of equipment to be operated by hand, which is the manual connection, or automatically by a pilot device, which is the auto form. There are versions of selector switches that are keyed so that only certain people can operate them, and that is those with the keys. You'll see that when you get into any elevator. There are selector switches that allow the fire department or public safety to be able to move the key switch, the selector switch, into an operation of the elevator that either keeps the doors open, that prevents other people from getting on the elevator during a fire or emergency or some other purpose. Now, as I said before, although we can use a keyed selector switch to turn off a piece of equipment so that it's not operated, that should never be used in place of correct lockout and tagout procedures, because in most every company, even the first failure of a technician to follow lockout, tagout procedures can result in that person being fired immediately from the job. There's another type of switch that's called a drum switch. Now, this isn't actually considered a pilot device all the time, but there are situations where it can be used as a pilot device. So we could, for example, have three-wire control to turn on power to a motor, but the direction of rotation of that motor can be changed by moving the lever of a drum switch. In an upcoming lab, or actually in a series of labs, you're going to be using drum switches to reverse the direction of rotation of an electric motor. Now, the way a drum switch works is that it reverses the polarity or the connections to various parts of the motor. In a three-phase motor, in order to reverse that, all we need to do is reverse any two of the three power connections. But we can also wire drum switches for single-phase motors or DC motors to reverse their direction as well. There are several layouts of the contacts in a drum switch. So you need to replace a bad drum switch with one that has the same internal configurations. Now this shows one of the possible ways of connecting. So when it's in the forward position, 1 and 2 are connected, 3 and 4 are connected, 5 and 6 are connected. But when it's in the reverse position, 1 and 3 are connected and 2 or 4 connected. When connected the way that you see below to a three-phase motor, that's how the drum switch is going to actually reverse two of the three phases of power that goes to the motor. And therefore, that reverses the direction of rotation of that particular motor. There's another pilot device called a limit switch. Now, sometimes we have pieces of equipment where there are moving parts, like a moving table or sliding a tool bit along the surface of a particular piece of material. So a limit switch is considered a mechanically operated switch. So it's operated not by a person pressing on it, as is a push button switch, or a person physically moving the contact connections like in a selector switch. But what it's activated with or activated by is something that is moving or something that is able to move. For example, the picture on the left shows a special saw that automatically can move the material back and forth to the correct location, and then the saw table will actually move. The saw blade stays in one position, but the table moves. Now we need to know when that table reaches the limit of its travel, and that's where a limit switch comes in handy. So the programming might be messed up, and it might think that the table has another 4 feet to travel, but in actuality you might have 18 inches. That selector switch will override what the controller tells the machine to do, and when it hits that limit, it stops moving, and that keeps the mechanisms from being destroyed if the movement is blocked or stalled. Now, what you'll see on the the right-hand side is a movable surface that moves back and forth as the motor rotates. It has a screw, a lead screw, that moves it back and forth. And what we can do is put a limit switch at the end of travel on the left and on the right side so that when the motor reaches the limit switch, it's turned off. Otherwise, the motor will want to keep turning, it will be stalled, it will heat up and burn up, or we could be breaking mechanical parts. If that motor is strong enough, it could snap the components of that movable cable. And as we said, the mechanically operated switches are not hand operated. They're operated automatically. So they serve as a switch because they're either on or off. But it isn't something manual that turns them on and off. It's some other force. In this case, there's an example of a pressure operated switch. So at a certain pressure, the switch will close or open. There is a temperature switch at which point at a certain temperature a contact will either open or close. And then in the lowest one, the one right in the middle, that's a limit switch, and it's operated by a certain position being reached, such as the limit of movement or travel on a piece of equipment that has a motion, linear motion back and forth, or maybe it's up and down. So essentially, a limit switch is a body that's made out of usually it's steel or aluminum, and that makes it strong and sturdy. Within it, it has contacts. Sometimes it has both normally open and normally closed contacts, so you can select which one applies to the circuit. And then it also has a certain type of operator. It could be an operator that is a roller or a lever that basically goes in and out of the limit switch body. It could be a lever that moves left and right, and that causes the contact to open or close. And again, this slide will show how we use limit switches to determine the limit, the safe movement, the safe travel zone of a movable surface. This is a picture at the right-hand side of what a limit switch might look like inside. You'll see that there's actually two contact blocks. So when we wire this one up, we can use one limit switch for a normally open application, or we can use the same switch and wire it for normally closed operation. Now, this is an important thing to remember about limit switches. Their normal state is with the lever, or it could be the plunger, whatever is the actuator. The actuator is not being acted on. It's not being moved or pressed or have any force on it. So that is its normal state. Now, sometimes we have them to where they stay in their normal state until they reach a particular limit of travel or something activates them. But there are other times when, under normal circumstances, the limit switch is activated, and then the abnormal operation then deactivates the limit switch. So when you see the normally open held closed limit switch, that means that they used a normally open limit switch, but the way it was mounted under normal circumstances, it's actually held closed. A good example of this, and I've used this example before, is on the door or access door of a piece of equipment. So when that door is closed, the piece of equipment can operate normally. But once somebody opens that access door, the limit switch that's mounted right behind that door will either open or it will close, and that will basically turn off the control circuit. So let's say you're using a piece of equipment, let's say a lathe or a mill, and the gearbox is enclosed with a door. Well, if you're using the piece of equipment and either on purpose or accidentally that access door is opened, then the limit switch that's either held closed or held open under normal circumstances, that changes its condition, and therefore the machine will shut down. And that keeps people from getting into the wrong places and having the ability to get their hands caught in a piece of equipment or their clothing to get pulled in. So it's a protection, a safety piece of engineering that's usually designed as part of the control circuit. Remember, when you see the symbol of a limit switch, when the lever is down, when it's facing down, it's either a normally open limit switch or it's a normally open limit switch that's held closed. When I look at this triangle, that means the actuator of the limit switch. So if I can push on that, then it's right now, if I can push on this normally open one, then it will close. Well, the normally open held closed, I can't push on that. It's already activated. So that's how I can tell the difference between a normally open held closed and, let's say, a normally closed one. The normally closed switches, their lever faces up on the schematic. That means when I press on this actuator on a normally closed switch, it can move and it'll open. Like this down here, the normally closed held open. But if I push on it, then it's only going to open more. It's not going to change its state. So you're going to have to be able to distinguish between a normally open and a normally closed held open. They look very similar, but notice that the levers are on the opposite side. And differentiate between normally closed and normally open held closed. Again, the lever is on the opposite side. We can get different actuators for limit switches, and sometimes we can actually change out the actuator or operator with a different type. And that essentially makes a limit switch to be a more universal replacement. This shows a limit switch that's normally open and one that's normally closed. This is the same switch, except we're using both sets of contacts. We're using the normally open set of contacts and the normally closed set of contacts. And so this just shows how that would work in a simulation. This is where we would put a limit switch if we wanted to have a piece of equipment move forward, and then when it reaches its limit, it shuts down or stops. And then when it's reversed, it'll also turn off when it reaches the limit of travel because it opens up that limit switch. Now, both of these limit switches, they're different ones because they're different locations on the piece of equipment. They're both normally closed, which means that until the limit is reached, the circuit will operate correctly. Now, this particular circuit has 3-wire control, but it has a forward and a reverse button, and it has a forward contactor, which is wired to make the motor move in the forward direction. Maybe that would be clockwise. And then the reverse contactor is a separate contactor that's wired to reverse the motor. So let's say reverse means the motor is moving counterclockwise. So this is how we can have a bidirectional, two-direction control circuit. Now, one thing also I want you to know is that when you see this R contact that's normally closed, when the reverse coil is energized, that will open, and therefore the forward coil will stop working, and vice versa. This forward normally closed relay contact will open up when the forward coil is energized. So when you're operating the motor in the forward direction, this F, normally closed contact, will open. You can push the reverse button all you want, but it will still run in the forward direction until the limit has been reached. And vice versa. You're operating it in reverse, but this normally closed reverse contact will open, and you can press the forward button all you want, but when it's operating in the reverse direction, the motor will not go forward. If you didn't have those, they're called interlocks. Sometimes they call those fail safes. If you didn't have those normally closed contacts, then you could conceivably try to run the motor forward and reverse at the same time. If you're running it forward and you press the reverse button, you're going to short out some of the electrical wiring that's part of the motor. You'll create a short circuit, things will blow up or spark, things will melt and burn, and there will be damage. So when we have a system that has a forward rotation or forward direction and reverse rotation or reverse direction, then we have to have a way of preventing someone from trying to change the direction of the motor rotation. There are versions of limit switches that are very small. They generally have plastic bodies, and they can be used in things like for doors, access doors to protect them, or if you open the cover, a protective cover of a piece of equipment to load the material into it, then the action of the mechanism will stop. And we can also use it for other devices. Printers, back in the day when we had inkjet printers and printers that would move back and forth on a carriage, one of the things that needed to happen is when you first turned it on, it would move that printing mechanism all the way to the end until it hit a limit switch. Then it knew exactly where the end was, and then that reset the counter that controls the motor location. And then it could go back the correct number of steps and be at exactly the right position. Sometimes they would put a limit switch on the left-hand side of the printing mechanism, and it would go all the way to that limit, and then it would reset, and it knows that if it stepped the motor 20 steps, then it would be at the edge of the page. So those are some of the examples of where micro limit switches can be used. Also on printers, you might have those that will show when there's paper in the printer. So when there's no more paper, that lever will be able to be moved up and it shows that you're out of paper. So there's a lot of reasons why we would use micro limit switches, and they're generally used in smaller pieces of equipment. A lot of electronics that have movement in them have limit switches built into their circuitry. Before we had automatic controllers, computer-based controllers, microprocessor-based controllers, we could have timers that had cams in them, and limit switches that followed those cams. So as it rotated, certain switches would close and certain ones would open. The symbol for that type of a timing switch, a rotating cam timer, is shown up here. It just shows the limit switches, but it also has that circle with arrows on each end showing that there is rotation associated with it. And you see the broken lines, those dashed lines. You'll remember that means that those things are mechanically connected but not electrically connected to each other. So far, we've talked about switches that are operated by a person, an operator, let's say, for a piece of equipment, or switches that have come in contact with a part of a machine or a piece of equipment. In this section, we're going to talk about other types of sensors that are automatic, that are used as pilot devices or sensing devices for a particular condition. Now, a lot of people use the term sensors to talk about both switches, which are discrete on-off devices, and types of sensors that make a measurement, an industrial measurement of some kind. Maybe it's temperature or pressure or flow rate or RPMs or pH or any number of things that need to be measured for process control to happen. So this device that we're looking at right now is a temperature sensor, but the correct way to talk about them is a temperature switch, because they are looking for a particular temperature, and when that temperature is reached, the switch will either turn on or turn off. Now, this is a proper use of the word switch because the output is discrete. When you see a temperature switch on the schematic, you notice that back and forth, almost zigzag-like pattern on the switch symbol. A common way of implementing temperature control by using a temperature switch is this device that you see here. There is a remote sensing enclosure that can be mounted separately or at a different location than the actual temperature measurement that's being taken. The way that this type of device can get temperature or the effective temperature into the sensing device is through what's called a capillary tube. A capillary tube is a very small diameter piece of tubing. Most always it is made of metal, and it is purchased with a particular distance of tubing. Let's say you buy one that's 3 feet long, you can get up to 3 feet distance between the actual enclosure that has the switch in it from the area that you're making that measurement. So inside the capillary tube is some type of liquid that will expand significantly when heat is applied to it. In the old days, we would use mercury, but because mercury is a toxic substance, they have switched to other chemicals. One of the chemicals was alcohol, but they have a mixture of materials that work really well in these devices now. Because the capillary tube cannot expand. And the end of the capillary tube, called the bulb, that comes in contact with whatever we're trying to measure that temperature, that doesn't expand either. But what is happening is that at the end of the capillary tube is something called a bellows. A bellows is like a balloon in the sense that as you add pressure to it, it expands. But the way the bellows is made is that when pressure increases inside of it, it only moves in one direction. Now, at the end of the bellows, we attach a rod, and that rod transfers the movement of the bellows to the contact block. So at a certain amount of pressure, the bellows will activate that contact and either open it or close it depending upon how the temperature switch is wired. Now, the main spring inside of the actuator or the sensing device, that is how we can control the temperature that will close or open the contacts. If we tighten the spring, then it will be a higher temperature that will cause the contacts to change. If we loosen the spring, it will be a lower temperature at which the contacts will change. So most all of these devices are adjustable, and by turning a screw, that changes the pressure on the spring, and therefore we can adjust which temperature we want the contact to either open or close. Now, this is a circuit that uses a temperature switch, and it's going to close when the temperature reaches a certain point. In this particular circuit, it's controlling a fan. And we also have hand-off automatic control where we can turn the fan on manually by putting the selector switch on the hand setting, or we can allow it to turn on when it reaches a particular temperature by putting it on the automatic setting. Now you'll notice that this is two-wire control, with the temperature switch being the pilot device. On the right-hand side of the schematic, you'll see the starter. In this case, it's a two-pole manual starter, which looks like a switch, a light switch on the outside. But on the inside, it additionally has a heater that will cause this starter to trip when a certain amount of current is sent through it. So we can protect this motor from an overload condition by the use of this starter. One thing to notice is that between the two contacts on the schematic diagram, the ladder diagram, you'll see that there's a broken line. That shows that one lever or one operator on that switch actually closes both of those contacts. There is a type of sensor or switch that's called a pressure switch. We can also get them to measure vacuum, which is really the absence of pressure. If you can think of pressure as a pushing force, vacuum is a pulling force. We can also get these pressure switches in the differential pressure configuration, and I'll tell you what that is on the next slide. You'll know that it's a pressure switch because the symbol will have a half circle. What differential pressure means is that that device has two inputs. It measures two different pressures, and it actually subtracts the lower pressure from the higher pressure, and that makes the difference. So that's why they call it a differential pressure device. One of the ways that we can use a differential pressure device is to see if a filter has clogged up enough to need to be changed or is too clogged for the circuit to work or the piece of equipment to work. So we'll put one side of the differential pressure connected to the duct or the piping before the filter, and we'll put the other connection into the duct or piping outside of that filter or the other side of the filter. When the filter starts clogging, there is more and more of a pressure drop because of the filter. When there is enough difference between the pressure going into the filter and the pressure coming out of the filter, then the differential pressure switch will either close a set of contacts or open a set of contacts. So we can have it to where it will turn on a pilot light to say it's time for a filter change. Or we could actually put it in the motor control circuit to where the unit will no longer operate if the filter is clogged up to that point. In order to use the piece of equipment again, we would have to replace the filter. Now, this is an example of a pressure operated device. It's basically an air compressor that's used to power air tools or do other things that need compressed air. If we didn't have the automatic control, someone would have to watch the pressure gauge and turn the compressor on when the tank pressure drops below a certain point. And then we would have to stay there and watch the gauge and turn off the compressor once it's reached the actual pressure that we want it to be. If we didn't do that, if we didn't have something to control the amount of pressure that goes into the tank, a couple things could happen. Most of the time, the tank has a bypass valve that will allow it to vent the extra pressure. But if that wasn't there, the tank itself could explode, or it could blow off the plumbing and the fittings, the piping, and everything that's attached to the tank. It could blow out the seals inside the compressor and damage it. It could stall the compressor and the motor will no longer spin, and then that overloads and overheats the motor. And if we didn't have a motor starter in that circuit, then the motor would just sit there and eventually start burning. So this pressure switch is very important, not only for safety reasons, but for the ability to operate this automatically. You can see here where the pressure switch would be on the circuit. There is an on-off switch so that the compressor can be plugged in but not operational. But when you want the compressor to work, you turn the on-off switch to the on position, and if the pressure in the tank is below the pressure set in the pressure switch, the contact will be closed. The motor starter coil will be energized and the compressor will run. When it reaches the pressure that you want, then the pressure switch will open up. Now, most of the time the pressure switch can be adjusted, but there are times when we don't want anybody to be able to change that. So we will get a fixed pressure switch with a fixed value. There's another type of switch which is called a float switch. What a float switch does is it uses the principle of buoyancy by using a float which is of less density than the liquid in which it's floating. So a float will do exactly what it's called. It will float on the surface of that liquid. The floats can be a metal ball or metal cylinder that is hollow on the inside and filled with air. It could be a rubber or a foam material. But what will happen is that when that float is attached to the switch assembly, when the liquid rises to the right level, that will cause the switch to either close or open. Now, this particular example on this slide is using a float switch in a sump. Now, a sump is a little indentation or cavity that is put into the floor of, let's say, a basement. And when liquid kind of flows in there, let's say it drains in from a leak in the foundation, at a certain level, the pump will turn on because of the float switch. And then once the liquid has dropped down below a certain level, the float switch will turn off. Now, we use float switches because we don't want the pump to continually cycle. If we had a sensor to sense that there was water, and any time that there was moisture or liquid there, the pump would turn on, then we could have the pump turning on and off constantly for a long period of time. That would waste power, that would wear out the pump quickly. So we create that cavity to store up enough liquid until it's worth the pump turning on. Now, if there's liquid flowing in there consistently, then the pump will operate almost continuously, and that's okay. But when there's just a little bit of liquid, we don't want the pump turning on and off constantly. We want to use it efficiently. So the liquid level builds up, and then at some point it'll turn on, and then after the liquid has dropped down enough, it will turn off. As you can see, a float switch is a full circle on its symbol, and that would represent the actual float device that's at the end of it. Now, this is an example of a single float switch used to control when the motor to the pump turns on to fill the tank. So this particular float switch has a range of motion. You can see on the bottom of the tank it says motor start. So when the level reaches that point, the contacts will close and the float switch will turn the motor on. And then the motor will stay on, the pump motor, until the level reaches the motor stop level. And then the switch will open and the circuit will no longer work. This particular float switch has a pretty decent range of motion. So it can control when the motor turns on and when it turns off. If the tank is much larger than the float switch is able to detect, then they will put two float switches. They'll put one at the bottom that will signal the starter to operate, and one at the top, and that will signal the motor to stop. So we can use a single float switch or several of them, depending upon the size of the tank. There's another type of switch called a flow switch. You can see the symbol, it has a flag on it. That flag is a good indication that it's flow. Basically, the way a flow switch works is it's like when you roll the window down on your car and you're driving down the road and you put your hand out of the window. When you're moving, the wind that's flowing past your car, because of its motion, will push your arm back. Now we can set these flow switches to where they will close or open the contact at a particular amount of flow rate. Or sometimes they just are set for a certain flow rate and you don't adjust them. They're used to check when you have a situation where it needs to be flow, but you don't want to operate that piece of equipment if there is no flow. An example of that would be a flow switch that works in conjunction with a burner or a boiler unit. If we turn on the burner and there is no flow, then we need to shut the system off because there is a fault somewhere. We can also use this to make sure that liquid is flowing in a chiller, because if we turn a chiller on to cool the liquid, but the liquid is not moving, then the liquid will soon freeze. And as you know, water, when it freezes, it expands, and that would damage or destroy the internal parts of that chiller system. So flow switches are used to make sure that there is a sufficient amount of flow for the equipment to operate. Here's a simple example of a flow switch circuit. It just connects a flow switch to a pilot light. But we can take that flow switch and use it as a pilot device to control a motor starter or some other type of motor control circuit. Even though this is simple, if you were to, in your mind, substitute the pilot light for a starter or some other control circuit, you can see where that would be placed. One thing to talk about is the word sensor is used so many different ways by so many different people. In theory, a sensor is a device that takes a measurement, that gives an actual digital signal or an electrical signal of the actual measurement. How many degrees Fahrenheit? How many gallons per minute of flow rate? How many inches of level? Things like that. But people also use the word sensor in a discrete device, which is either on off. Theoretically, you want to call all of those devices switches, because that is the function of a switch, is to either control current going through it, turning it on, or stopping the flow of current by turning it off. So when a sensor is in a circuit, it's used to either detect, which would mean that it is going to close or open a contact, or it's going to measure something. What a sensor does is it converts some type of input. It could be mechanical, it could be magnetic, it could be thermal, it could be either light or color, it could be some type of a chemical condition, such as the acidity of the liquid that it's measuring, something like that, into either voltage or current, or it could be just the flow of current in a switch. And what they're doing now is that a lot of these sensors have been built with converters in them that make digital data that the computers understand that are connected to them, or the controllers. Now, this is one use of the word sensor that is commonly accepted, but it's rather incorrect. A proximity sensor is actually a proximity switch. I call it a proximity detector, because what it does is to detect the presence of an object close by the sensor without having to make physical contact with it. So if you take a look at the symbol below for a normally open proximity detector, then you'll see that it looks like a limit switch. And it functions like a limit switch in the sense that when something is in that area, it will either turn on or turn off. But in this case, you see that diamond that encloses it, and that means that there is no physical connection between the sensor and the device that it's detecting. There are two different types of proximity detectors. One is called an inductive type, and the other is called a capacitive type. If you're sensing the presence of metal, then you can use an inductive type sensor. They're less expensive and they operate very well as long as the object can come close enough to the sensor to be within range and the object is made out of some type of metal. What they do is they create a pulsing magnetic field that is focused to the end of the sensor. And then when an object that's metallic comes within the range of that magnetic field, it's actually going to change the characteristic of that magnetic field. Inside the sensor, you have four different parts. The oscillator basically turns electrical current, which is DC, into pulses of voltage. It does not necessarily need to be alternating current. It can be just pulses of direct current. When that goes to the coil, which is an electromagnet, those pulses make a magnetic field. Without anything in the magnetic field's realm of influence, in other words, if it's not close enough to be inside the magnetic field that's being generated, the oscillator will operate at a specific frequency. So there are a definite number of pulses per second that occur. However, when that object comes in contact with the field, not the device, but gets inside of that field, then the oscillator will not be able to create the pulses at that same frequency. It will slow the pulses down. And what happens with that is that when the detector circuit sees that the oscillator has changed frequency enough, and we do that so that it's not super sensitive, because if we had it very, very, very sensitive, then it would not be very accurate. We could have false readings. So the detector needs to see a certain amount of change of frequency of the oscillator. And once it sees that, then it closes a contact in the output part of the circuit. Now, I say it closes the contact because you're used to thinking about relays and contacts closing. But in reality, what that output actually is a transistor. A transistor is an electronic version of a relay contact. So when the transistor is turned on, current will flow through it, much like current flows through a closed contact. Now, it's important to know the type of metal that you're using, because if it's a ferrous metal, which contains iron, cast iron, for example, or steel, then they can be a little bit further away from the proximity detector than other metals that are non-ferrous, like copper or brass or aluminum. And then those have to be closer. Now, one of the things that you'll see on this picture is the term hysteresis. Hysteresis is something that is used as a term in a number of different applications in electronics. Basically, hysteresis in this case is what point does it detect, and what point does it stop seeing that object and stop detecting it? So when the object comes within the magnetic field and it reaches a certain position, the detector will detect it. But it can then move out of the magnetic field a little bit before it stops detecting. So the difference between detecting and non-detecting the position is called the hysteresis zone. There are 3-wire proximity detectors and there are 2-wire proximity detectors. Now on the upcoming test, you're going to have to figure out how to wire a 3-wire detector and a 2-wire detector. If there's a 3-wire detector, then that's pretty easy to operate and wire. It has a positive input for the positive connection to the power supply. It has a negative input, which is the negative lead of the power supply. And then it has another wire that when the sensor is activated, there will be current flowing through that third connection. Depending upon the type of transistor that's used inside of the proximity detector, you connect the load to either the negative side on the opposite end of the third wire or the positive side. And in this case, the load is connected between that third wire and the negative connection. Proximity detectors are DC devices, and when we talk about a load, we could use a relay coil as a load. We could use a pilot light or anything that would use the electrical power in the control circuit. Now, a 2-wire proximity detector, it can work on AC or DC. And essentially what happens is the load allows a little bit of current to flow through it. And that little bit of current is called leakage current. And that leakage current is enough to activate the internal electronics in the proximity detector. It's not enough current to cause enough magnetism to close the relay contact, or enough current to cause the light to glow if it's a pilot light. So the load has to allow current to flow through it in an off state or in a standby state. But then when the switch is activated, it will actually create a path that has very, very low resistance in it. So therefore, the correct amount of current will now flow through the load, causing it to activate. The problem, as you could see with inductive sensors, is they can only detect metallic objects, conductive objects, objects that will conduct electricity. This capacitive sensor can detect cardboard cartons filled with things. It can detect plastics. It doesn't even need to be like a plastic water bottle filled with liquid. It could be an empty bottle. It could be actually a part that was made out of plastic that was going down the conveyor belt. They work differently. Rather than having a magnetic field, they have a static electricity field. They look just like inductive sensors, but you have to really know which ones they are. You have to actually look at the device, and the device might not even say, so you might have to look up the part number. So if you're replacing a proximity sensor or a proximity detector, you have to make sure that it's the correct type. The way a capacitive one works is the static electricity field that is focused on the end of the sensor interacts with the object that's in front of it. It's like what you learned about with capacitors in basic electronics. A capacitor, the amount of capacitance or the capacity of that capacitor is determined by a couple of factors, by the area of the plates and also by the distance between the plates and also by the type of dielectric or insulating material between the plates. In this case, it's a very poor capacitor and it doesn't oscillate in the electrical circuit. The frequency of oscillation is really the function of that capacitance. However, when you put an object in proximity of a capacitor sensor, that object becomes part of the capacitor. It actually makes a much better capacitance, and the oscillator will oscillate. It will make its waves of electrical energy. So the detector circuit in a capacitive type proximity detector looks for oscillation. When the oscillation is sufficient, then it registers that as an object being in proximity to the detector. We can use photoelectric sensors kind of like we use proximity detectors. They don't require a contact, but basically they're looking for the object visually. And essentially what we're doing is we're sending a beam of light, and it's either being interrupted when the object is in front of it, or it bounces off the object when the object is in front of it. When you've gone to a small store, maybe a coffee shop or someplace, and you walk through the door and you hear a doorbell ring or a chime go off so that lets the people working there know that a customer has walked in, this is the same type of device that we're talking about. That uses a beam of light on one side from a transmitter, a light source, and it uses a sensor or receiver on the other side, which is a device that senses light. And when the beam is broken, that creates the tone so that they know that somebody has walked into the store. These photoelectric sensors kind of do the same thing, but they're just looking for specific points of light that are being disrupted. They often use LED laser lights, or they may use small lasers themselves. That's because those devices can really focus a beam of light in a very sharp point, and that can mean increased accuracy rather than just using a regular light source. Even with a lens, we might not be able to get that fine of a point. A majority of these use the receiver and the transmitter in the same package. So light comes out of the transmitter hole, light enters in the receiver hole. The light is not a solid beam, but rather it's a series of pulses. In one type of system, it's called retroreflective scanning. Both the transmitter, the light source, and the receiver are on the same enclosure, in the same module. The light comes out of the transmitter and it hits a reflector or a piece of reflective tape and bounces back to the receiver. So when the object comes across that beam and breaks the beam, then the switch inside of it will close or open, showing that it detects an object there. We can use them for a variety of different applications. But anytime that we have a situation where the beam is interrupted, then we can use this type of scanning technique. And it doesn't necessarily need to be objects going across a conveyor belt. It could be pieces of the equipment, and that we use these instead of a limit switch or some mechanical switch. One of the problems with retroreflective sensors is that if the object that's going across that beam of light is reflective, it could reflect the light back and not see the fact that the beam was broken by that object. The way that they can solve that is to actually use special filter lenses that will cause the light waves to be polarized. In other words, their waves will be in the same direction. When it hits the reflector, then that will cause the light waves to change their direction. So the receiver filter has a different polarized system. It's polarized differently. Now, when an object gets in the way that's reflective, it's going to change the wave of the light particles. It'll bend them to a different direction, but it will not bend them to exactly the direction that the reflector would. So that filter, the polarized filter, can filter that light out. Or if we have other situations where uh, we have multiple ones of these close by, we don't want light from one of them to bleed into the other one. So we can use those polarized filters to make sure that we are accurate. Now, if you're replacing one of these, you need to make sure that you replace the filters, take it from the old device and put it on the new one. There is another type of scanning called diffuse scanning, and it actually uses the object itself to bounce light off of. Now, they don't need a reflector, so what happens in this case is when the object is not there, there is no light that bounces back to the detector. But when the object comes into the light beam, the light hits it, it may be scattered in a bunch of different directions, but at least some of that light will be reflected back into the receiver. So in this case, we're not looking for the absence of light like the other two types. We're looking for light that is reflected back, and that shows that there's an object there. Now, this can also work when we have objects not only that are shiny and reflective, but we can use those, if they're very sensitive, to read colors. Some colors absorb the light and other colors reflect the light. So we can make sure, for example, that a part is positioned correctly when the reflecting part of that object is reflecting the beam back. If it's incorrectly placed or in a wrong position and the light does not reflect back, then we know that it's in the wrong position. So here is a review of the three types. Through beam has the transmitter and receiver on opposite ends. The beam is broken. That shows that the object is there. Retroreflective has the transmitter and receiver on the same side, and a reflector or reflective tape allows the light to bounce back. When that light beam is broken by the object, that detects that the object is there. Now, diffuse means that light is hitting the object and bouncing back. And there is no reflected light when the object is not there, but there is light reflected when the object is there. So that's opposite of through beam and retroreflective. We can use fiber optics if we wanted to have the emitter and the detector in the sensor located away from the device being measured. Maybe it's really hot in there. It could be corrosive. It could have dangerous chemicals. There could be other reasons why we would want to locate the sensor further away from the object than it normally would be. So fiber optics is not really a scan technique, but it's a way of getting the light to there and from there. There's a lot of advantages of fiber optics. You can see those advantages on this screen. This is how the fibers would be configured if we had through beam or retroreflective or diffuse scanning. There are some fibers that have one direction and only one light source. Those would work for through beam, but there are others that the end of it has two fibers connected to it. There's a type of sensor called a Hall effect sensor, and what it looks for is a magnetic field. Hall effect sensors are used in a lot of different places in your vehicle, especially if you have a modern late model vehicle. But they're used in all different types of devices. They're also used to sense the amount of current that's flowing through a particular part of a circuit or in a electrical panel or a distribution center. The distribution connections, the panel boards. What they do is they will change their state. They actually act like little switches that when a magnetic field is in its presence, it will turn on or off, depending upon the magnetic field that's there. If there is north-south fields that are changing just like what you see on there, it will actually make pulses of electricity as the magnetic field changes. It'll turn off and then back on every time the polarity changes. They're made from a semiconductor material that is sensitive to magnetism. There's a type of Hall effect sensor that is actually a true sensor. It will change its characteristics as the measurement is being changed. Now, what we're measuring with a Hall effect sensor is the strength of a magnetic field. So if we put a wire that carries current in the middle of a ferrite core. Now, ferrite is basically powdered iron that has been compressed under high pressure and temperature, and it becomes a solid object. We can use it to mold the correct size that we want. But that ferrite core basically takes the magnetic field around the conductor and focuses it. There is a little cut or a gap in the core, and that is where the Hall effect sensor is placed. As more current flows through the conductor, more magnetism is created. As more magnetism is created, the Hall effect sensor will get a greater voltage, will generate a greater voltage. So the amount of voltage is proportional to the amount of current that's flowing through the wire, which is basically caused by the increasing magnetic field around the conductor. That's how we can measure DC current with a clamp-on ammeter. The old clamp-on meters used a coil of wire as a transformer. It was like a current transformer that we talked about before. it's just a loop of wire, and when the magnetic field builds up and collapses in an alternating current carrying wire, it will induce a little bit of voltage in that coil. Well, now we can buy meters, clamp-on meters that make no physical contact. You just clamp them around the wire, and we can measure not only alternating current, but we can measure direct current as well. And that's because of the advances in Hall effect semiconductor technology. Another use of a Hall effect device is that we can measure the position of a rotating object. We can also measure the speed of that rotating object. If we were to put little gear teeth on that object, or a piece of magnetic material, or even just if we put the magnet inside the Hall effect device and have a piece of ferrous material, which is either iron or steel, when that little tab or the gear tooth goes across the Hall effect sensor, it generates a pulse of electricity. If we measure the frequency of the pulse, we can mathematically calculate the speed of rotation. We can also use this to cause something to happen at a precise time. For example, they would use this in an automotive engine, a gasoline engine, where each spark plug had to fire at exactly the right time. If it was an 8-cylinder vehicle, they would have a gear tooth in the distributor that has 8 teeth. Each tooth represents a cylinder and when that cylinder needs to fire. So as that tooth goes across the Hall effect sensor, that puts a pulse of electricity into a step-up transformer that's called the ignition coil, and that makes 30, 40, 50,000 volts that then is put into the correct spark plug. Even devices that work on modern vehicles where they have their own ignition coil for each spark plug and they're fired by the computer, how they know when it needs to be fired is with a Hall effect device. There's another form of sensor that's used to measure level. It's also used to detect an object in front of it. It's called an ultrasonic sensor. The ultrasonic sensor uses a sound frequency that is higher than the human ear can hear, and probably even dogs, their hearing frequency. What happens here is that it uses the principle of sonar. Sonar is the type of device that's used underwater to determine the depth of the ground below it, or that's used to detect other objects in the water, like the enemy submarines. In this case, what happens is that it sends a burst of sound waves, and that those sound waves hit a surface and are reflected back. The amount of time it takes for the sound wave to leave the sensor, bounce back, and return to the sensor is recorded and measured. And then that is converted to a distance measurement. So from that, we can actually sense the level of liquid in a tank, or we can sense the presence of an object, maybe the amount of powder that's sitting in a bin. As long as it's a surface that can reflect that sound back, we can measure it. One of the uses of an ultrasonic sensor is kind of like a proximity detector, in the sense that if you have objects on a conveyor belt, when that object comes in contact, or I should say in front of that sound wave, then it will bounce back at a different speed. So it's good for us to use when it's a transparent object and we can't use light waves as in the photo detectors, or maybe a capacitive detector might not work with that particular amount of uh, plastic and solids or glass and solids. So this is also sensing a particular location or proximity with an ultrasonic sensor. Now, when we talk about temperature sensing devices, I'm only covering these because they're in the textbook and the worksheets. I'm not going to go into detail because this is a topic that's covered a lot better in the instrumentation classes. So what we're going to talk about is just an overview. One of the ways of measuring temperature, particularly high temperatures, is that we can take two different metals and turn them into wire, and we'll take the end of those two wires and either bond them together or twist them together tightly. What will happen is that as the heat makes the metals expand, one of the metals will expand faster than the other. So I think of that kind of like a hand squeezing a sponge. The one that expands faster is like the hand. The wire that does not expand as fast is like the sponge. And the liquid that comes out of the sponge is like the electrons that come out of the thermocouple. A thermocouple basically makes a very small DC voltage. That small DC voltage increases as the temperature increases. Now what you'll see here is a hot junction and a cold junction mentioned. The hot junction is where the two pieces of wire are bonded together, and that's the end of the probe where it is in proximity of the heat that's being measured. The cold junction is actually what happens when those wires are connected to a terminal or some other type of wire or some other connection. That will also create a little mini thermocouple junction. So there's actually making a little bit of voltage at the connection point of the thermocouple to the device that it's being connected to. So what happens is that the voltage that's generated in the hot junction is actually, it needs to have the voltage from the cold junction deducted from it or subtracted from it in order to get an accurate reading. Here's a bunch of information, and most of this is beyond the realm of this class. But just know that there are two different metals that are used in the two different wires that are bonded together in a thermocouple. They make a very small amount of voltage. There are different configurations, a type K configuration at 300 degrees Celsius, which is well over 400 degrees, will produce a very small amount of voltage, 12.2 millivolts, or 12.2 thousandths of a volt. So there needs to be some type of amplifier that will take that very tiny amount of voltage and make it into a measurable amount that the sensor will understand. There are a couple of different types of thermocouple ends, and they're shown here. They're often put in some type of a enclosure, a tube, a sheath to protect them. Sometimes the actual element comes out of the end of the sheath, and they would call that an exposed type. There's another type of temperature sensor called an RTD. Those are very common in industrial environments and in the oil fields and other industrial or energy related fields because they're very um, accurate. What they have inside of them is a special metal. It's a very fine wire. Oftentimes, it's smaller than the diameter of a human hair. And that wire is very long because it needs to be long in order to work effectively and accurately. But what they'll do is they'll take that long wire that's very, very thin and they'll wrap it around a piece of ceramic material. And that allows us the opportunity to have a long piece of wire, but focus that on a very small end of the probe. RTDs will increase their resistance as they get hotter, whereas some other devices decrease their resistance as they get hotter. This case, it's called positive temperature coefficient. The hotter they become, the more resistance they will have inside of them. Here's an example of an RTD used as a temperature sensor connected to a controller. So we can either heat the material or cool the material depending upon what temperature we're measuring. They are really common in industrial environments because of their uh, temperature stability, the fact that they have a large range of temperatures that they can detect, and they're very accurate and very stable. So you can have repeatable measurements throughout the life of the RTD. It doesn't change much at all over its lifespan. There's another type of sensor called a thermistor. Now, they're a resistor that itself changes resistance when temperature is acting on it. So they are usually negative temperature coefficient. So, in other words, what happens is that as the thermistor heats up, its resistance drops. So these are good for types of sensors where we just want to sense a particular level. It doesn't have to be super accurate. They will embed these into motors and to where we can, let me see if we can look back at the motor circuits. Nope, don't have it. Well, anyway, a lot of times you can buy an electric motor with a thermistor that is embedded into the coil itself. So as the motor heats up, that thermistor is taking a measurement of the temperature. And we can have a special switch that senses when the actual heat of the motor reaches a certain point, and it's like a thermal overload. Sometimes they'll even use thermistors inside overload starters instead of mechanical devices. You have a heater inside of the starter. The thermistor measures the heat coming from that heater, and at an overload condition, the thermistor will close or open a contact, usually opening a normally closed contact, and it will allow that circuit to shut off. Thermistors are really used because they're cheap. They're very inexpensive, and they're not very accurate, but there are times when we need to sense temperature, but we don't need super accuracy. We can buy thermistors that are built into an integrated circuit, and that contains all of the electronics that are necessary to make them function as a full sensor. There are times when we need to make sure that the motor itself is operating at the correct speed. For example, when we use a type of motor controller called a variable frequency drive, we can use that drive to make that motor go at a certain speed. However, the drive does not know for sure that the motor is going at the right speed. So sometimes we buy a motor that has a built-in tachometer or some other type of position and rotation sensor. So in this case, what happens is that as the motor rotates, the tachometer makes little pulses, and those pulses are then converted into a speed signal that goes back to the controller. That allows the controller to know that the motor is going exactly the speed that it wants it to turn. Now, sometimes we can use a magnetic pickup, which basically is connected to the shaft of the motor. The pickup itself does not touch the rotating part. The rotating part actually has little teeth like a gear, and every time one of those gear teeth goes across the coil, it generates a pulse of electricity. That's kind of like the Hall effect circuit that we were talking about, except that this is a whole lot less technical. It's just a coil, it's a magnet, and as that tooth goes across the pull piece, the magnetic field is pulled across the coil, and that generates a pulse of electricity. So by measuring the frequency of those pulses, we know the speed of the motor. If we have two of those that are located a little bit offset from each other, then we can compare both pulses and we'll know which direction the motor is spinning. So they will call that a directional sensor as well. Another type of sensor is called an encoder. One thing that they use with an encoder is the same system like you would see in a light beam sensing system, like we were talking about, a photoelectric system. So there is a light source, and on the opposite side, there is a detector. The motor shaft is connected to a disc that is actually clear, and it has lines drawn on it. And every time that it goes past a line, the light beam is interrupted. So what's really cool about this particular one is that it is very sensitive, and it knows exactly the position, how much the motor shaft has rotated. Not only the speed of the shaft, but its position because of the pulses that it is counted. So let's say when it goes 90 degrees of rotation, let's say that means that there is 100 pulses. And so that it will know, hey, I'm exactly at 90 degrees. If there is 50 pulses, I'm at 45 degrees. If there's 200 pulses, I've gone 180 degrees. So this allows for precise positioning. They use those a lot in robotics back in the day when we wanted to have the motor spin to a certain location, but we wanted to get that feedback that shows that the motor was actually at the position. Because if the motor was interfered with, if maybe there were, some objects or something that caused the motor to stall a little bit, you still gave it the signal to move the full amount, but it actually did not move the full amount. That could be disastrous in robotics and automation. So there is usually some type of an encoder built into the motor itself, whether it would be a servo motor or a stepper motor. And that's the two motors that we will talk about in just a little bit. There is a type of flow measurement device that actually measures the amount or rate of flow. And that's also called the flow velocity. And there is a whole lot to these and how they work. That is covered in great detail in the instrumentation class. But basically what I want to do is just talk about a couple of these common flow measurement devices. A turbine one uses a little wheel inside, and as that wheel moves, the blades of the wheel generate little pulses. Those pulses are measured and actually counted, and by counting the amount of pulses in a given amount of time, they can register the gallons per minute. There's another type called a target flow meter, and that actually kind of works like the flow switch. And when I was talking about that, I said, okay, when you roll your window down and your vehicle is going down the road and you put your hand out, the faster you're going, the further it's going to push your hand back, the more pressure is acting on your hand. And so that's the version of this. It has a plate that the flow hits, and that causes the plate to move. The greater the flow rate, the more motion of that lever that's connected to the plate. There is another one that's called a magnetic flow meter. Now that it kind of seems like magic how this thing works. It makes a magnetic field, and that causes the molecules inside the liquid, as long as the liquid is conductive, it causes those molecules to align electrically. That creates a little bit of voltage in that liquid, and sensors measure that voltage. So as the flow rate changes, then the amount of voltage that is sensed will change. So more flow rate means more voltage being generated. There is no physical device, there's nothing in this sensor or this flow meter that is in the path of the liquid. And that makes it really good because it doesn't restrict flow. There's nothing mechanical to wear out. It's all electronic. And as you could imagine, these are very expensive compared to other sensors that measure flow rate. Now let's get into actuators. An actuator is a device that converts electrical energy into motion, either a straight line motion or a rotation. The difference between a motor and an actuator is that an actuator does not continually rotate. It does not have 360 degrees of rotation and can keep doing that. If it's a rotational actuator, it will move less than 360 degrees of rotation. There are a couple motors that we're going to talk about. They're not, they could be called actuators because they cause a movement of something in the device or the piece of equipment, but it's not. One type of actuator that's very common is the solenoid. The solenoid simply is a coil of wire with a movable plunger that can be pulled inside of it. When the coil is magnetized, that attracts the plunger into it. It pulls it in, it sucks it in, and that will cause motion to occur. Now, generally, a solenoid has a very short movement, a short distance of travel, but usually that's enough to do things like close contacts or move a lever or do other things that will cause something mechanical to happen. And its symbol looks like a part of a resistor symbol. There is a difference between AC and DC solenoids. You can't mix them up. You can't use an AC solenoid with a DC power supply and vice versa. AC ones tend to pull in more powerfully, and it tends to, it's more powerful in the fully open position, and as it pulls in, it becomes less powerful. They're usually faster than DC. The problem with an AC solenoid is what limits the current through the coil is the presence of that piece of metal in the movable part, the plunger. So if a solenoid is not allowed to move completely in its range of travel, if it doesn't pull in completely, then it could overheat and burn up. Now, a DC solenoid will have the same strength throughout the entire range of motion, and it's just not going to overheat like an AC solenoid would if it's not completely pulled in. It's a lot more quiet than an AC solenoid because in an AC solenoid, the coil vibrates with the frequency of the alternating current. There are ways of making it quieter, but it's still, if you put your hand on it, you'll feel vibration. You won't with DC because the current is flowing consistently. They're more accurate in repeatability, in making sure that when every time they're energized, they have the same pulling force and exert the same mechanical load. There are rotation type solenoids or rotary solenoids that are like motors, but they move a partial amount of rotation. So we can use those to, like for example, that you see up there, we have a conveyor belt where there is a junction or a Y in that conveyor belt. So we can select which outlet we want the material to go into. So that rotary solenoid can move that little directional piece of metal back and forth to make the material go in either of the sides. Now there are a couple different ways of a solenoid operating. We can have a solenoid that has the coil itself move. We can also have a solenoid where the internal part that's either a magnet or a piece of metal that's made out of steel usually will be located. So either way, we have different methods of moving the shaft inside the solenoid. One of the things about a solenoid is this moving coil actuator allows us to position exactly where that shaft is. That coil is called a voice coil, and it's very similar to the coil and the setup inside a speaker. But instead of being connected to a cone that makes sound waves, that coil is connected to a shaft that makes motion. So in the old days of automation, they would use moving coil actuators sometimes rather than motors and gear sets to be able to have a precise linear motion. Now there's a type of valve called a solenoid valve, and essentially has a solenoid on it, but when the movable part of the solenoid is moved, it opens the valve, or it could close the valve. It changes the state of it. You can buy solenoid valves that are normally open and some that are normally closed. But remember, on a valve, open means that it is on, but in a switch, open means that it's off. Closed in a valve means that the valve is off. Closed in a switch means that the valve is on, or the switch is on. So rather than turning a handle, a screw handle, and opening the valve that way, the coil just pulls the stem of the valve out of the way. Or it could pull it into and plug that opening. Now, one of the things about solenoid valves is they all have a direction of flow that's indicated by an arrow on the valve. If you put them in backwards, they may not operate properly. You're not going to get the precise control like you would if it were correctly installed. They're commonly used to control the flow of liquid. So a solenoid valve is either open or closed. Generally, a solenoid valve is not used to control a position of a valve, but we can just completely open it or completely close it. This is the circuit that is shown for this particular application, where we have two sensors that will check to see if the tank is empty or the tank is full, and it will either activate a solenoid to put liquid into the tank or empty liquid from the tank. So we can maintain a particular range of levels in that tank. So if you look at this circuit, you'll see that there are two sensors. These sensors, as you see, are drawn as though they are proximity detectors. We can use a proximity detector if it's a capacitive type as a level sensor, but they're doing that to make it a little bit easier for you to understand. Now, the solenoid A is the fill tank solenoid, and solenoid B is the empty tank solenoid. There's a type of actuator called an electric linear actuator. There are times when we want to move something a pretty significant distance. They'll use these to move TV screens up from the inside of a cabinet. They'll use those to open doors or close doors. They'll use them to do things around the production facility where we need linear motion, straight line motion, but we need a longer distance, a longer stroke, a longer distance of travel. And oftentimes there'll be motorized actuators. So this particular one has a motor and has a drive belt that gears down the motor rotation so that the actual screw part of the actuator goes at a slower speed. Now the way these work is there is a lead screw. A lead screw has threads on it like any fastener, except they're threads that are cut a little bit differently so that we can transfer motion. So there is a nut that has the same type of thread as the lead screw. The nut is attached to what needs to be moving back and forth. In this case, it's a block of material. But in other cases, it's the actual rod that moves in and out of the actuator. So the lead screw rotates, but it doesn't physically go out or in. It's held captive. The nut will move back and forth. Here's another version that has the motor built in line with the lead screw and the shaft of the actuator, the rod. Now, there are actuators that are called um, valve operators or electric operators for valves. They're motors with a gear system inside of them so that we can rotate the motor, put power to the motor, and that gear reduction will cause the little disc inside the valve to rotate. As that disc gets more in parallel with the flow of liquid, as it opens more, then we'll get more flow through that valve. So rather than taking a valve and having to manually turn an, a wheel or rotate a knob, these electric valves do that with electricity into a motor that's then gear reduced, and it opens or closes the valve. A relay is a type of an actuator, so in a sense it converts electrical signal into mechanical movement. So we have a solenoid associated with a relay, but what the solenoid is doing with that motion is it's closing contacts or opening contacts. Sometimes we have a system where the coil itself will cause an arm to move. That moving arm is called the armature. When the electromagnet is energized, the relay coil is energized, that will move the armature in and the contacts will close or open. There are other kinds of contactors that use a solenoid, and then the relay contacts are off to the side and there's mechanical movement between them. In a future lecture, we're going to get more into the makeup of relays and the types and the applications. In this case, we're just looking at relays as a device. In this case, we're using a proximity switch to energize a control relay. When the control relay is energized, then the motor will operate. That turns on the motor starter. Now let's get into a couple of the motor types that could be considered actuators. One is called a stepper motor. And a stepper motor, when the coils are energized, it doesn't rotate completely. It doesn't continuously rotate. It will move the middle, the rotating part, one position, just a tiny little bit, and that movement is called a step. So if we energize the coils in a particular order, then the rotating part, the inside of the motor, the armature, is actually going to follow that magnetic coil movement, as you see on this animation. So a stepper motor is more like on a clock when the second hand ticks, whereas other motors are like a second hand that would sweep, that would continually rotate. This is rotated by a series of pulses to the correct coil at the correct time. When you buy a stepper motor, you're going to buy it with the voltage and current or resistance setting, but you're also going to see how many degrees per step. So if I take a stepper motor that requires 60 steps for a complete rotation, then I take 360 degrees divided by 60 steps per rotation, and that gives me how many degrees per step. So if you replace a stepper motor with one that has a different number of degrees per step, then it's not going to function at all like you want it to function. Stepper motors, you just don't connect them to the line. They need a drive. They need electronics that are going to energize those coils in the correct sequence. Most of the time, the stepper motor is used in an open loop system. There's no feedback, there's no encoder or sensor on the stepper motor to tell the controller exactly that it is in the position that it thinks it is. So it's rotating that stepper motor blindly, and it's trusting that the stepper motor is where it thinks it is. That's open loop. Closed loop would be having that sensor giving feedback to the controller, telling it exactly where it is, exactly how many degrees of rotation has it rotated. Steppers are used a lot for precise positioning of devices. The problem is that they don't produce a lot of horsepower. The early robots, the robotic arms, the robotic welders, things like that would use stepper motors, but they were limited in the amount of power those motors would produce. So they've switched to a different type called a servo motor. Now, a servo motor is a motor that can be run all the way down to 0 RPMs with full power, full torque to that. Generally, what's a servo motor system has that feedback. The term servo is used in a lot of different applications in electronics and motor control. The term servo means that there is a sensor that is giving position feedback to whatever is controlling it. For example, when you move the ship's wheel, the steering wheel of a very large ship, you're not moving the actual rudder of the ship. What you're doing is creating an electrical signal from one motor, which is like the generator. It's connected to the ship's wheel. And then there is a different motor that is at the rudder that's really huge. So the motor at the rudder follows exactly the same position as the ship's wheel. So that was one of the earliest servo systems. For us in motor control, a servo motor has a feedback mechanism. It has some type of a position sensor or a velocity sensor or a tachometer or something that shows that the motor is doing exactly what the controller thinks it is. So they are closed loop control with servo motors. The great thing about servo motors is that you can get them in a fraction of a horsepower, less than 1 horsepower in size, all the way up to dozens of horsepower. So we can create extremely powerful automated equipment using servo motors. There's a lot more to servo motors that we'll talk about later. And some of these differences are not going to be talked about in this particular presentation, but when we get further into it. A brushless DC motor is a common type of motor that's used for servo motor systems. It's like a regular three-phase motor, but instead of the middle part being just a cage of coils or of little loops, it actually is a permanent magnet that has different polarities as you go across the surface of the magnet. This is how a brushless DC motor operates. The rotor is the part that is magnetized. The stator is the part that is literally not moving. And that part has the coils in it. Now in this case, this is showing the type of brushless DC motor that you see at the upper left-hand corner. where the rotor is on the outside and the stator is on the inside. In the motors that we use, it's the opposite. The stator coils will be on the outside, and in the center will be the magnet that is being rotated, called the rotor. But can you see that as the stator coils are energized magnetically, the magnetized rotor will follow those magnetized stators, or those energized stator coils. So we have electronics that actually energize those coils in the correct rotation, the correct sequence, the correct direction, the correct speed, all of that. So with the motors that we have, this servo motors will not operate without a controller. We cannot connect them directly to three-phase power and have them work like we want them to, because of the way that they're built. However, when we put a servo controller attached to that motor, they have the most precise speed control of all of the motor types that we would normally look at. And as I said before, because the coils are independently energized, if we wanted to lock that shaft of the motor solid and have it not able to spin, have 0 RPMs of rotation, we could still energize those stator coils and the motor would stay locked in that position. We just wouldn't change the stator coils, their energizing and the pattern. We would just leave them energized the way that they were when the motor was stopped. And again, you have Hall effect sensors that help provide the feedback to make sure that the motor itself is operating correctly. A great thing about servo motors is because they can be synchronized with a controller or with other mechanical sensors and devices, we can use them for precise positioning. So that concludes our presentation for this topic, motor control and motor terminology. Thanks for listening.